Section 10.11 is called cooling methods. So with all this that's going on in the transformer, we've got to provide a uh, mechanism, I guess to say, to dissipate the heat that is building up in this device. And so there's some pretty sophisticated design consideration that goes into some of this, but we'll look at some just general examples and notice that the larger the transformer gets, that the more complex the cooling method has become. And we'll explore some of this. You don't need a lot of information from me. You might say that's true for any of this, but the I just thought I'd sort of direct you through the reading of this. So we're told in this section that indoor transformers, and again, think about all the different considerations that have to be made for this for these electrical machines, right? And where they operate, the operating environment is one of the primary ones. And so here we're specifically talking about indoor transformers, and we're talking about indoor transformers that are less than 200 kVA on their rating. And so they can be naturally cooled by natural flow of surrounding air. And the housing, the metallic housing of the transformer um, is fitted with these ventilating louvres that he calls these things here, right? And so the air can circulate and flow over the windings in the core, and um, you know it works well for that. This particular one is a 1500 kVA, 600 volt in, 240 out. So this would be something after the main service. You'd have main service out here coming in to our transformer here, and it brings it down to here and brings it, and then that is fed into here. And from here, this might be something that we have inside our facility because it's in these operating voltages. Now it is three-phase, of course, three-phase electricity, but it's inside the building, right? So this might be something that you actually interacted with. And again, that tired old thing about if we were in the lab, I have lots of these great examples in the lab that we could look at. I've got keys to the cabinets and all that. We can look inside of it and see all this. Um, but anyway, this would potentially be an area that we played in. Okay, larger transformers can be built the same way, but we need some sort of forced circulation of clean air. Um, One is, the dry type transformers are used inside buildings that are away from hostile environments. But distribution transformers below 200 kVA are usually immersed in mineral oil and enclosed in a steel tank. The oil carries the heat away to the tank where it's dissipated by radiation and convection, something we talked about in terms in ELC 135. Oil is a better insulator than air. Consequently, it is used on these high voltage transformers. And here's that, and we're kind of used to seeing these, right? This is 75 kVA, and it actually shows that on the casing, and it shows that's the nominal rating, and it also shows the primary voltage that is associated with that. Now the output for this is given as 240 volts, which is a very useful voltage for us at our facilities. And again, a lot of this depends on what you're trying to do. Other things that are given are the temperature rise here, right? The frequency. There's an impedance of 4.2%. Small radiators on the side, okay? These are little radiators, they give more exposure to the air, and they are built there. So this would be, that type of radiator that would have, transformer that would have this mineral oil immersed in it. And then as the power rating increases, the power rating increases, external radiators are added. Okay, so we're looking at in this area here, in terms of what that is. Um, External radiators are added to increase the cooling surface of the oil-filled tank. Oil circulates around the windings and moves the heat, and then the heat is released to the surrounding air. For higher rating, cooling fans blow over the radiators, etc. So, we see that all this changes. This is a 1900 kVA, so different area here that we're talking about. Um, Voltage 26,400 kilovolts. Now, beyond this, for transformers in what we talk is the megawatt range, cooling may be affected by an oil water heat exchanger. Hot oil is drawn from the transformer tank and pumped to a heat exchanger where it flows through pipes. And I think we have some pictures of those too. And they're in contact with cool water. Such a heat exchanger is very efficient, but it's also very costly. And let's see, are we ready to look at one of those? Yeah, okay, 220, figure 1018. Okay, so this is what we're looking at here, a combination of hot oil and then this actually, this looks like a big HVAC type unit, right? Where we're, actually using the cool water that, surrounds this to take the heat out. Then there are still other types of transformers. Look at this. This is 1,300 megavolt amps. Goodness, 1.3 gigavolt amps. Huge step up transformer, right? So we're going to step this up from 24.5 kN. That must come from the actual generator itself. And we're stepping it up to 345,000 kilovolts. Now, we know enough from reading our other book that we are almost finished with. We have one more chapter. We want to transport the electricity at the highest voltage possible to eliminate I squared R losses across the conductor line. So that's why we step it up. And then there's some other information about that. And let's see, what else do we have? Let's see, some big transformers designed to have multiple ratings depending on the type of cooling that's used. Okay, a transformer may have a triple rating of 18,000, 24,000, 32,000, depending on whether it is cooled by natural air, forced air, or some sort of forced circulation. So you can actually increase the operating parameters of the transformer based on what type of cooling that you use. Okay, so here is a three-phase OA, FA, FOA. What does that mean? Well, on page 208, we see that OA means oil immersed, self-cooled. FA must mean forced air some way. Yeah, it does. And FOA is forced air, forced oil cooled. Okay, so it's rated at 3 different based on whatever the type of cooling that is used in association with it. Okay, temperature rises, those are something that we have to consider when we look at it. And let's see, what else does he say? The temperature must be kept low to preserve the quality of the oil. By contrast, the temperature rise of a dry type transformer may be as high as 180 degrees C, depending on the type of insulation used. Okay, bottom line takeaway. The larger the transformer, the bigger the heat considerations are, and the more elaborate these cooling methods are that are needed to keep this electrical machine operating properly and safely and efficiently.